We will be briefing you about power angle equation of a synchronous machine. These are my teammates, Pushkar Pratanjali, Madhurya S, myself Akshita Ganesh and Akshita M. First we'll start off with the basics. Let's look at the equivalent circuit model of a synchronous motor. I'll explain the terms on this diagram that you see here. RA is the armature current, XL is the armature leakage reactance, XAS is the synchronous reactance, ZS is the synchronous impedance which accounts for both RA and both the reactances. VD is the applied voltage or the terminal voltage, and IA is the armature current per phase. All the values that are given here are per phase. Now we'll apply Kirchhoff's voltage law to get the equation for VT and EF. VT is equal to IARA plus JIAXL plus JIAXAS plus EF. Combining the reactances, we have XS is equal to XL plus XAS. Now condensing the equation, we finally get VT is equal to EF plus IAZS. The phasor diagram of the equivalent circuit model. Now we have VT as the reference phasor, and IA is the armature current which lags by 5 degrees, and using the current through the resistance RA will be in phase, so we draw it along IA, that is IARA, and perpendicular to it is IAXS. Using triangular vector addition, we get EF, which is the excitation voltage, or you could also call it the counter EMF. We get it as VT minus IAZS. The phase angle delta between the terminal voltage VT and the excitation voltage EF is called the power angle. The angle that you see here in this phasor diagram, which is named as delta. This delta is what we are briefing you about. It is called the power angle or the load angle, or also could be called the torque angle.
Okay, I'm Madhurya, and except for very small machines, the armature resistance of a synchronous motor is relatively insignificant compared to its synchronous reactance. So the previous equation, EF is equal to VT minus IAZS, can be approximated to equation 2, which is VT is equal to EF plus JIAXS. The equivalent circuit and phasor diagram corresponding to this equation is shown in the next slide. Okay, these are normally used for analyzing the behavior of a synchronous motor due to changes in load or due to changes in field excitation. Now this is a phasor diagram model for a synchronous motor where we are assuming that RA is negligible. From this phasor diagram, we have that IAXS cos theta I is equal to minus EF sin delta because they are parallel lines. When we multiply throughout by VT and rearrange the terms, we have VT into IA cos theta I is equal to minus VT EF XS sin delta divided by XS. This is equation 4. Now since the left side of equation 4 is an expression for active power input and we are assuming that RA is negligible, the power input will also represent the electromagnetic power developed per phase by the synchronous motor. Therefore, from equation 4 we get that P input per phase is equal to VT IA cos phi I, which implies that P input per phase is equal to minus VT EF sin delta by XS. Similarly, for a 3-phase synchronous motor, we just have to multiply the equation, the RHS by 3. So we get P input equal to 3 VT IA cos theta phi I, or P input is equal to 3 minus 3 VT EF sin delta divided by XS. Now equation 6, 7 and 8 is called the synchronous machine power equation, and it expresses the electromagnetic power developed per phase by a cylindrical rotor motor in terms of its excitation voltage and power angle.
I'm Akshita and I will be continuing. So assuming that a constant source voltage and constant supply frequency, the above equations of 5 and 6, which is power input per phase and which is equal to VT IA cos phi, can be written as
may be expressed as proportionalities, and this is very useful in analyzing the behavior of the synchronous motor. From equation 5 we get power input per phase is equal to Vt Ia cos phi phi I, and thus power is directly proportional to Ia cos phi, and from equation 6 we get power is directly proportional to Ef sin delta. This is the equivalent circuit of a synchronous motor, and as you see the resistance is assumed to be negligible and hence does not feature in the diagram. Moving on to effect of changes in the load on the power angle diagram of a synchronous motor. Looking at the phasor diagram, the terminal voltage is taken as a reference, and the armature currents Ia1 and Ia2 are lagging at an angle of phi I1 and phi I2, and using the triangular vector law and completing the vector diagram, we get the excitation voltage If1. This will be further explained to you by Pushkar.
Okay, this is Pushkar and I'll be talking to you about the effect of changes in load on the power angle of a synchronous motor. Basically, along with the power angle, you also have changes in the armature current and the power factor of a synchronous motor, quite obviously from the phasor diagram shown here. If we look at the phasor diagram here, the effect of increasing the shaft load if we choose to increase the shaft load to twice its initial value, which you can see is represented by the light lines indicating the new steady state conditions. Here these are drawn in accordance to the given equations above. So when the shaft load is double to both Ia cos phi and Ef sin delta are both doubled. So basically when you redraw the phasor diagrams to show new steady state conditions, the line of action of the new JIA-XS phasor must be perpendicular to the new line phasor. Furthermore, if you look at the excitation, is not really changed here. So increasing the shaft load causes the locus of the EF phasor to follow a circular arc. Along with that, if we look to choose the armature current, power angle and the power factor of a synchronous motor, if you want to see its effect and variations, if we increase both the angle of lag and the counter EMF phasor, the magnitude of the stator currents stays as there. So it is interesting to note that during all these load variations, however, except the duration of the transient conditions, the motor assumes a new position in relation to the rotating magnetic field. So therefore, the average speed of the machine simply does not change. So if we look to increase the load here, a final point comes if we choose to increase the load here, the final point is reached at which a further increase in delta fails to cause a corresponding increase in motor torque, and the rotor pulls out of synchronism. So basically, if we have a change in the delta, that is the power angle here, and if it is increased to a point where it cannot sync up with the motor as well, the simple rotor falls out of synchronism out of the machine itself. So in fact, if we look at it, the point of maximum power angle where it reaches approximately 90 degrees for a cylindrical rotor machine, as indicated, it can cause this synchronous motor to pull out when this delta value is approximately 90. So basically, the delta equal to 90 will pull the rotor out of synchronism as such. So as from this here, we can see that we have talked about the effect of power angle, and along power angle we have talked about the armature current and the power factor. So this is basically the power angle equation of what we have explained by my 2 minutes. So thank you.